Welcome back. In this lecture I will be talking about the language of propositional logic, that is we will be focusing our attention on syntax. Any language will have its own syntax and semantics, and then the relationship between in logic what we will be doing is that we will be talking about the relationship between syntax and semantics. Syntax has something to do with the proofs, whereas semantics is something to do with the truth. So let us begin with what is considered to be the language of the minimal things that we need to know before proceeding further. We need to know something about the notation, etc. So any language will have its own alphabet. An alphabet of propositional logic consists of these things. There are infinitely many propositional variables such as p0, p1, p2, etc., pn. So many things are available to us so that we can represent sentences. The basic units of propositional logic are considered propositions or sentences. Propositions, sentences, all these things are used in the same way as long as propositional logics are concerned. So of course there are some debates as to what exactly you mean by a proposition, especially when you move to modal logics. We will be talking about possible worlds, etc. But till then, as of now, proposition, sentences, statement, etc. are all same. A proposition is considered to be a sentence which is either true or false. So we cleverly choose these sentences in such a way that they are either true or false. That means you can clearly draw a line between, for example, let us say mortal and non-mortal. That is why if you observe classical logic, the examples are quite clear, where you can clearly draw a line between what is the case and what is not the case. Something is true and something is false. Those things which can be spoken as either true or false are under our purview. So there are many things which you cannot spoke about those things to be true or false. For example, if I ask someone what is your name, or shut the door, or you are expressing some kind of emotions, etc., there is no way in which you can talk about whether the sentence is true or false. There are commands or some kind of questions, etc. So logic can be used in three different ways. It communicates something, information, etc. That is the one which we are using it. And the second one is it evokes some kind of emotions. The third one is it talks about some kind of commands, etc. So we are not interested in the other two things, but we are interested in declarative kind of statements such as the sun rises in the east, or this chalk piece is yellow in color, etc. So we have infinitely many propositional variables representing all the propositions, and we have logical connectives. These are the things which we have: negation and or, and implies, and if and only if. And just like in the case of English language, we need to have some full stops, commas, etc. So in this case this is only used for our convenience, otherwise we will have some confusion in reading the formulas. So we have left parenthesis, right, left bracket, and then full stop, brackets, and right parenthesis, and we usually write p, q, r's, etc., propositional variables. And there are two there are two symbols that we will be using it: bot, ulta t, that stands for those sentences which are always false or contradictions, and t, those sentences which are always considered to be true are represented as t. So there are tautologies. So if we can classify our sentences, it can be like this, that there are some tautologies, and there are contradictions. They are always false. Tautologies are always true, and there are some sentences which are sometimes true, sometimes false. They are called contingent statements. So now we have these alphabets, and then we know how these alphabets combine together and form some kind of strings, meaningful some kind of strings, which are considered to be well formed formulas. Just like in the case of English language, we have no alphabet, whatever alphabet we have, it will not combine and form a meaningful word. So CAT makes sense to us, TAC for example, and make any sense to us. In the same way, in the case of formal logic, in the case of propositional logic, these strings will combine in certain way and form meaningful kind of things. So these are the definitions that we have. How can we say that a given formula is considered to be a well formed formula? These well formed formulas are generated by P, Q, R, and then the logical connectives and implies R, etc., and then we have parenthesis left bracket and right bracket. So every propositional variable is considered to be a well formed formula. Suppose if you write P and Q etc. is considered to be a well formed formula, and these logical constants like top and bot are obviously well formed formulas. And if there are two well formed formulas phi and psi, then anything which you combine in this way, only in this way will become well formed formula, otherwise it is not considered to be a well formed formula. For example, if phi and psi are well formed formulas, obviously conjunction and disjunction are also considered to be well formed. This is a routine kind of thing that we will be noticing in this case. So the language of propositional logic is like this. It consists of A, B, C, some formulas which consists of propositional variables, and then something which is considered to be contradiction, negation of A, and A and B are combined with the help of conjunction A and B, A or B, A plus B, and A if and only if B, where P ranges over a countable set of propositional variables and whose elements are also called as propositional symbols or propositional variables. We also let Q and R to range over propositional variables. So formulas of the form single formulas like bot, top or P are considered to be atomic propositions. So these are the propositions. These propositions combine with the help of logical connective and form compound propositions. For example, A is a atomic proposition, B is another atomic proposition. These two may combine in various ways and form atomic sentences like A if and only if B, which is interpreted as A implies B and B implies A. There are some kind of conventions that we follow in the case of propositional logic, and these are like this. We do not use excessively this outer parenthesis etc. You can just simply remove it. For example, you have a formula like this, P R Q implies R. You do not have to use this outer brackets, and you can simply talk about it as this thing P R Q R R. So outer parenthesis can be simply removed from this one, and there is another way in which is important here, that is this. There is some kind of order of precedence that we follow, that is like this. First you start with negation and conjunction, disjunction, implication, and if and only if. So why you require these things in the case of propositional logic? For example, if you have a sentence like this where we do not know where we need to put our brackets. In any good textbook in logic, it will have all the parentheses given. Suppose if you don't, if somebody writes a formula like this, then there are two ways in which you can read this formula. The first way is that P R Q implies R, that means P, it is combined with another statement with R, P R Q implies R, or you can read this statement in a different way, that is P R Q implies R. So these two formulas are totally different. So how can we say that when you have a formula like this, all of us read it in the same way? So that is why we are following some kind of conventions. So these conventions, the conventions that we follow is like this. So the idea here is that every formula in propositional logic has its own tree structure. Suppose if you draw a tree diagram for a given formula, it looks different for different formulas. If it looks same, then these two formulas are considered to be logically equivalent to each other. So here are two formulas that we have. Now we do not know how to figure out how to draw parenthesis here. P R Q implies R. So now if you say it is P R Q implies R, and it has some kind of tree structure, and if you say P R Q implies R, this will have its own structure, tree structure. So every formula comes up with its own corresponding tree structure. No two formulas will have the same kind of tree structure. So this formula needs to be represented like this. So now we give some kind of reference to these connectives. For example, if you have a formula like this, now how do we write in a proper way? So now the first preference should be given to negation, which is not there in this formula, and the second preference should be given to R. So now wherever this R occurs, you just put a bracket like this. Now the next preference should be given to and is not there here, implication and if and only if. So now we have implication here, and then you put bracket here. So that is the way in which you can read this particular kind of formula. So these two formulas, P R Q implies R and P R Q implies R. So these two have different kind of structure. So this needs to be read like this, P R Q, and then so this is R. So this is considered to be the tree structure for this one. It has to be read like this, P R Q implies R. So now for this it is like this. So R, P and implies and Q and R. So this is the way you can draw a diagram for these two things. So this stands for this, P R Q implies R. That is the way you read the formulas. So every tree ends with atomic formulas. So these two diagrams are different. That means every formula will have its own tree structure. No two formulas will have the same kind of tree structure. So this is the convention that we follow, but in most of the logic textbooks, all these parentheses are given. If it is not given to us, then how do we read the formula in the same way? We follow this precedence. First you give importance to the negation, and then followed by that and, or, implication and if and only if. Another important thing you need to note is that in our order of preference, we started with this thing and R implies and if and only if. So now in any given formula, let us say it is P implies Q if and only if R. Suppose if you have a formula like this, then the lowest precedence that we have is if and only if. So now this will become the major connective. So why we are talking about this precedence is just to find out what is considered to be a major connective in our given formula. So while constructing the truth table, this is considered to be very important. So the one which occupies the less precedence is considered to be our major connective here. So this way you read out the formulas in propositional logic. The same thing applies when we talk about modal logics. We can still talk about the same kind of thing. Another important thing you need to notice is that binary connectives like R implies and etc. are considered to be right associative. They always operate on a right kind of thing. So we have something called as sub formula, particularly when any given formula occurs in any other formula. For example, if you have A implies B and C, B and C is one formula, and then total A implies B and C is another formula. So B and C is considered to be sub formula of that thing. For example, if you have this thing not P and then all these brackets etc., we indicate this reading by writing all the parentheses. It is like this, not P and Q implies not R or P etc. So this will look like this thing. Suppose if you have a statement like whatever is you are seeing it in point number 2, bullet number 2, we give first precedence should be given to the negation, then followed by that and then implication etc. Then ultimately this formula becomes like this, as you are seeing it in 3. So this way we construct in this way we can say that any given propositional logic will have its own syntax, This syntax is generated by these 5 logical connectives: implication, negation, and or etc. Thank you.